Hey friends, so this is our last lesson in regular calculus, volumes of revolution, and it's not mathematically a whole lot harder than anything else we've done. Everybody can get scared, the last lesson is going to be the hardest lesson or it's going to be the most abstract or something like that, and I don't really think it is. There's a little bit of abstractness in it in that you need to catch the visual of what we're talking about. But then the way we calculate it is gonna feel very, very familiar with you. So I'm thinking this is a non-stress note. I think it's a good way to end our time together, and it pieces together a couple of different items. So that's kind of cool too. So we're gonna look at volumes of revolutions. I'm gonna go back to this trusty old trapezoid that I've shown you a lot in this unit. Remember our friendly function f of x equals 3x plus 2 from 1 to 3. Here's the thought. What if I took that area and I spun it around the x-axis? Okay, I took that area and I spun it around the x-axis. So this is my very poor attempt at telling you I'm going to spin it. But what happens is we end up with a shape like this, okay? So I took this area, this was my original trapezoid, okay? And when I spun it around the x-axis, I ended up seeing it down here. Now I see it in 3 dimensions though, right? It's not just that I reflect it because I've spun it. So I actually see a circular shape here, okay? Okay, so we want to find out the volume of this shape, and this is what we're going to try and work on together, okay? Oh, let me get that ink off for you. Okay, so recall, to find the area under a curve, we found the sum of an infinite amount of rectangles between 1 and 3, and this formula that I used here, the very first one you see, would be Riemann's sum, right? The limit as n approaches infinity of the summation of f of x subscript I increment of x from I being 0 to n minus 1. But then after we did Riemann's sum, we realized, hey, that's actually just the integration of f of x from a to b, from our left bound to our right bound, okay? Awesome. Now, let's think this through. We will use a similar process to determine the volume of a figure obtained by revolving this area about the x-axis. If we rotate this elemental strip above the x-axis, what shape is produced? Well, the shape that we produce is actually a cylinder, okay? Where f of x would represent, I want you to think that through before I show you the drawing. Here's what I originally gave you. Right? Now, at any point in time, if I took a strip of this out, I'm looking at a cylinder. Now, some of you are bothered, I think, I can just feel it in the airways. Some of you are bothered by the fact that this is smaller than this. But remember, when we were looking for, think of it this way for a sec, just so I can kind of put your mind at ease. When we were looking for area, we looked at the area as a bunch of rectangles stacked on top of each other, right? An infinite amount of rectangles actually stacked on top of each other. And that's where that formula came from. That's where Riemann's sum, that's how Riemann's sum worked. Well, now it's the same thing. If I take one tiny little strip here, it's going to be a cylinder. So I'm looking at the with a bunch of cylinders stacked on top of each other. Okay, and just like here, the rectangles got larger as I kept stacking. With the cylinders will get larger as I keep stacking. Okay, so it's the same setup. Okay, now one little cylinder here, what would f of x represent? So f of x would be this length from here to here, right? That would be f of x. Well, if I had that spun round, do you see that that actually is the radius of my cylinder, okay? Then what would the increment of x be? Well, remember the increment of x was found down here. It was this distance here, right? Okay, so the radius and then each of those increments would actually end up being the height of the cylinder that I'm trying to find the volume of. Okay? Okay. So here's a better picture. I was just trying to get you to see it in your own head before I showed you. But essentially, if I take that strip out and I spin that strip around, I'm going to create this cylinder where the height of the cylinder is the increment of x and the radius of the cylinder is f of x. Okay, so now we're just going to build a formula. We know that the volume of the cylinder is V equals pi r squared h. But we just talked, okay, and we know, sorry, don't want to get ahead of myself, and we know this Riemann sum, or that to calculate, instead of using Riemann sum, we could have calculated by taking the integral of f of x. The integral of our original function will give us the area embedded from the curve to the x-axis. Okay, so now we're going to take these pieces and we're actually just going to put them together. Okay, we've now decided that r, the radius in this instance, would be f of x, and we've decided that h in this instance is the increment of x. Okay, so I can say volume will equal pi times f of x all squared times the increment of x. Okay. Okay, cool. Now the volume of the entire solid, this whole thing, is the sum of all the cylinders stacked up side by side each other. Our most accurate answer always occurs by making the width or height, that increment of x, to be as small as possible. Okay, which is the same as saying we're trying to squeeze as many disks into the regions as possible. Okay, so that is to say we should take the integral. Okay, for a solid disk, the volume actually becomes, the volume is the integral of pi f of x squared from a to b. Now, it's interesting to note here, and before I even keep reading, I want you to kind of think this through. It becomes the integral of pi f of x squared. Well, we just said f of x was the same as r. So it becomes the integral of pi r squared, right? F of x is my radius in this situation. So pi r squared, well, that's the area of a circle. Well, it should make sense. Just think this through for a second, because I want to have a little bit of time for some things to click in your head. It should make sense that if I integrate the area, I get the volume, because if I integrate something that's degree 2, I should end up with a degree 3 item, right? So it's the integration of the area that gives us the volume. When I was just looking for area, we were integrating the function to get the area. So we were integrating kind of like a one degree item, which was essentially the height of the rectangle each time, right? But we were integrating a 1 degree item to get out a 2 degree answer. Now we're integrating a 2 degree item to get out a 3 degree answer. Now I get that it's more complicated than that, because like I'm not trying to confuse you when I say a 1 degree item either, because some of those curves that we were doing weren't 1 degree. That's not what I'm trying to say. I'm trying to think about that space underneath, okay? I'm just trying to think through that space underneath to try and get you to feel comfortable with why we're integrating the area of the circle. The integration of the area of the circle gives me the volume of the cylinder, okay? So since a single slice of the solid generated always forms a circular disk, this formula applies in all cases, okay? Just like with Riemann sum, a single slice of that just formed a line, and then we integrated it and got the area of the rectangle. Now a single slice forms a circle and we integrate it and get the volume of the cylinder, okay? All right. If that message kind of was helpful to you, you should rewind and listen again. If it wasn't helpful to you, just keep going. Okay, so we end up with volume is the integration of the area, okay? Because area was pi r squared for a circle. Okay, so let's put this into practice. and try a question. Determine the volume generated by revolving or rotating the region under f of x equals 3x squared plus 2 from 1 to 3 about the x-axis. So we're still with that trapezoid I showed you at the beginning. We're going to rotate it, and we're going to try and figure out the volume. Okay, so I end up with volume equals the integration of pi f of x squared. I'm just going to put the pi in the front, okay, and we'll deal with him at the end. F of x is 3x plus 2, so now I'm just looking at 3x plus 2 squared. Okay, so 3x plus 2 squared, let's figure out what that is. That'd be 9x squared plus 12x plus 4. Okay, and now I just need to integrate that. Now, when I go to integrate that, I'm going to integrate each part, okay, but there is a pi in front of it all, so that pi would have to, the integration that I do would have to be in brackets, okay? So the integration of 9x squared, the x squared becomes a cube, so I'm looking at 3x cubed. I'm looking at 6x squared and 4x. Okay, so now it ends up being pi times that, and I'm evaluating that from 1 to 3. Okay, we're evaluating from 1 to 3. So that means I'm going to plug 3 in, and then I'm going to plug 1 in, and I'm going to subtract them. Okay, when I go and plug 3 in, it's going to look like that. When I plug 1 in, so now you're just doing the math. Okay, this part's a little bit more mindless. You don't have to think as much. Typing all that in, you should get a volume of 134 pi units cubed. Leave your answer in terms of pi, okay? 134 pi units cubed. Okay? See, that's not bad, really. Once you understand where we're coming from, it's still just another integration, okay? Okay, so determine the volume generated by revolving or rotating the region under f of x equals root of x, and this time we're going to go from 0 to 3, okay? But same sort of process. The integration will be pi times the root of x squared from 0 to 3, the integration of the root of x squared, sorry, from 0 to 3, okay? The root of x squared is x. The integration of that would be 1/2 x, or sorry, yeah, 1/2 x squared. Okay, I got a little ahead of myself. And then I'm going to evaluate 1/2 x squared from 0 to 3. So I'm plugging in 3. 3 squared is 9, so that's 9 over 2 minus 0. So that'd be 9 pi over 2 units cubed. Okay, 9 pi over 2 units cubed. Okay, so that's one thing we can do. The other thing we can do is we can have a hole in the center, okay? So instead of a solid disc, we get this, a washer or a donut shape. Donut sounds that's a much better visual than a washer, I don't know. Okay, washer is much more technical though. Determine the volume generated by revolving or rotating the region between f of x equals 3x plus 2 and f of x equals the root of x from 0 to 3 about the x-axis. Always begin by sketching the curves. So this will be our first example that has this donut-like structure or this washer-like structure in it. What happens is when I spin this, we end up with the revolved shape as actually a hollow bowl. And so one single slice looks like a washer instead of like a disc, okay? Well, think back to when we looked at volumes of, like, for instance, let's go play the donut game for a second. If I asked you for the volume of a donut, wouldn't you have gotten the volume of the whole thing and then minus the volume of the hole inside that you don't see, right? That's all we're doing here. That's all we have to add to this picture, okay? So if we're looking at something like this, when I spin it, okay, so here's my 3x plus 2 and here's my root x. So when I spin it, I get this hole created essentially by where that root x was spinning, okay? And so I get this shape that is a washer. Well, the increment of x is still the height of the washer. F of x is still going to be the radius, but now I have two different radii, to deal with. I have the outer radius, the outer edge radius, which would be my first f of x, and then the inner edge radius, which would be my second f of x, okay? And we've already integrated things where we had to take functions and subtract them from each other before we integrate. So really, this isn't new. It's just in a new context, okay? So let's just establish that then. The area of the washer would be pi times the outer radius squared minus pi times the inner radius squared, which would mean the full area would be pi times radius subscript 2 squared minus pi times radius subscript 1 squared. We've already talked about the fact that the volume of the washer is pi times the integration of the area, right? So to determine the volume of the disk, we end up with volume equals pi times the integration of f of x subscript 2 squared minus f of subscript 1 squared, okay? Where f of subscript 2, that would be the function that goes to the outer edge, and f of subscript 1, or f of x subscript 1 would be the function that goes just to the inner edge, okay? All right, so let's go back to this question that I started and we'll just piece that together. So we end up with the volume will equal pi times the integration from 0 to 3 of 3x plus 2 squared minus root of x squared, okay? Nothing else has changed. We just have to subtract the functions before we begin. But when you look at this question, I could have given this question to you in the last lesson or in the lesson before that. Like, you've done integrations that look like this. We're just going to clean it up and then we're going to integrate each section. Okay, so 3x plus 2 all squared would be 9x squared plus 6x plus 4 minus x. Okay, so then that becomes 9x squared plus 11x plus 4. And now I have to integrate that. Okay, so 9x squared integrated would be x cubed, 9 divided by 3, so that's 3x cubed. Then we've got 11 over 2x squared and 4x. Okay, and now I'm going to evaluate that from 0 to 3. So I'm plugging in 3, I'm plugging in 0, I'm subtracting them. This should be old hat. New hat, I don't care. Easy. So I plugged in 3. I plugged in 0. I'm good to go. Final answer ends up being 285 pi over 2 units cubed. 285 pi over 2 units cubed. Okay? That's it. That's all you got to do today. And that's all, folks. You guys are probably too young to realize that reference, but that's okay. If you do, let me know. You're heading up to page 408, which completes the book. I hope this has been a wonderful journey. As always, as you're reviewing this and other things as you prepare for final exam, you know where to find me. I'm only an email away. Please connect with me. I've had a lot of fun doing this course with you guys, and I hope you guys have had fun too. I hope you guys have learned a few things. I hope you're feeling a little bit more comfortable about calculus in general, and that it's not as scary as you perhaps head off and take this in university now. Okay, you guys got this. Take care.